So hello, everyone. It is a pleasure to welcome you to today's IAIFI Colloquium. It's a pleasure to have Rose Yu joining us to give today's colloquium. She is an assistant professor at UC San Diego in the Department of Computer Science and Engineering there, and is a member of the Data Science Institute at UCSD. She's primarily in the AI group, but is affiliated with a number of other institutes there. And she has interests generally across machine learning, but especially at the intersection of physics and machine learning, which is how many of us have already gotten to know her in various different contexts and whatnot. And so we're going to hear a good bit about many aspects of her work today, especially as it regards spatiotemporal data. And it's just wonderful to hear about your work, Rose. We're very excited you're here. Please take it away, and questions will mostly be held for the end, although some people might chime in partway through. We also have people following on YouTube, and there will be an opportunity for them to ask questions, which I will relay. Thanks.
Thank you so much, James, for the invitation and for the great organization of this talk seminar. So my name is Rose Yu, and I direct the Spatiotemporal Machine Learning Lab. Here is a logo of our lab. So there is a hidden letter S and T in the picture of Rose. So that stands for spatiotemporal. Let me give you a few examples of what I mean by spatiotemporal dynamics. Here's a video showing the temperature variation of the entire Earth for the past 50 years. So we all know that climate models are fundamental tools for improving our understanding of global climate. But climate models are basically a complex suite of partial differential equations. They're very difficult to simulate at high resolution. So right now, our climate model are still limited at 10-kilometer resolution, and we still cannot simulate, for example, hurricanes and these kind of dynamics. So nowadays we have access to, vast amount of data from satellites, and we also have new tools from machine learning. The question is, can we combine the new data and the new tools to develop better climate models? The second example is in the world of transportation. So again, in transportation, traditional methods rely on first principle modeling. These models rely on very strong assumptions of drivers' behavior. So we have this video shows you the traffic flow in the city of LA from morning to the evening, and the bubbles represent the accidents happening in the city of LA. So with advancement in sensing technology, we have all types of sensors, loop sensors, and camera sensors on roadsides that can record data at high frequency in real time. So the question is, can we leverage this type of data and combine that with first principle methods to develop better traffic models for self-driving cars, for road planning and congestion control? So as you can see now from these two examples, the data that we have is not image data in computer vision or text data in natural language processing, but in fact, it's a very special type of data that contains rich space and time information. So this type of data is actually ubiquitous in many science and engineering fields, from public health to climate science, transportation, and even quantum chemistry. So the mission of our research group is to develop machine learning methods that can drive insights from spatiotemporal data, and that's what I mean by learning spatiotemporal dynamics. So when we think about spatiotemporal data, a lot of them actually come from certain physical systems. So it's very natural to think about traditional physics-based methods to model spatiotemporal data. So in the past few years, our group has been working on this direction called PhysicsGuided AI, which closely integrates with the theme of this seminar or the general organization. So we know in physics, we use first principle methods to describe space and time patterns. We rely on model-based approaches to discover patterns in the data. In physics, we have tensor networks, which is what I did my PhD on, differential equations, and even symmetry to understand the behavior in space and time. So physics-based methods encode our domain knowledge. Therefore, they're very sample efficient, but they can be computationally expensive because of the first principle modeling and doing numerical integration. And sometimes physics-based methods can also be too rigid that are very far away from real-world data. And this sometimes we call model misspecification problem. On the other hand, we have machine learning, which is a statistical inference approach. So in machine learning, we typically use what is called data-driven methods to discover patterns from data. So in machine learning, we have computationally efficient methods, such as graphical models, neural networks, or deep learning, and variational Bayes to discover patterns from space and time data. But machine learning is data-driven, which means they also require a lot of data. So they have high sample complexity, which is a big issue now in science and engineering applications. Additionally, machine learning models are also known as black box models. They don't provide interpretation or explanation of what's happening in their predictions. Most importantly, I would also want to argue that when we apply machine learning methods to science and engineering problems, a lot of times the predictions of model are not physically consistent. So it's very hard for our scientists and engineers to trust the machine learning models if we cannot provide scientifically valid and physically consistent predictions. And as you can see now, the both field of physics and learning have complementary strengths. So the idea of physics-guided AI is to combine the best of two worlds together. And in this way, we can encode our domain knowledge as inductive biases into machine learning models. We can improve the generalization of physics-based methods to unseen scenario and new environments. We can reduce the sample complexity of learning. And most importantly, we can increase our trust in artificial intelligence, especially for science and engineering applications. So in today's talk, I'm going to sketch 3 different types of approaches that we can combine physics and learning together towards physics-guided AI. Before I do that, I was wondering whether any questions on the chat or on YouTube?
None yet. None yet on YouTube.
Okay. Great. So let's start with the first paradigm, which what I call trainable operator. So in this case, we want to learn spatial temporal dynamics. So we're given input time series, x1 to xt, where each state xi, xt can be a high dimensional vector that collects from multiple locations or just multiple features. And what we want to learn is a mathematical operator that can be parameterized by a deep neural network that give us a mapping from some xt to some yt, where yt can even be the next timestamp of the prediction, which is xp plus 1. So if we can successfully learn this underlying map, then we say we learn the underlying dynamics of the system. So in mathematics, we have an operator that is familiar to a lot of us, which is the Laplacian operator. So this operator will convolve the input function f of t, right, using the operator e to the power minus xt, so that compute the Laplacian operator. Then the idea of trainable operator is that, well, instead of manually designing this function f of t, we can just use a deep learning model to approximate this operator and then use the coefficients to decide how we can compute this operator. Right? It gives much more flexibility of the mathematical operator while pertaining to the original principles of this operator. So that's the idea of trainable operator. And this f of t can be fully parameterized as a weight in the neural network. Let me show you an example of accelerating turbulent simulation. So we know that turbulence is so fundamental to climate science. As in a sense, here you're looking at the simulation of a turbulence known as the Rayleigh-Bernard convection. So it happens when the cold fluid in the top interacts with the warm fluid in the bottom, which creates very intricate patterns. This resembles the dynamics of El Nino, where the warm fluid in South Africa starts to interact with the cold fluid in North America. So to simulate this video alone would take several months. And our goal in this project is to develop deep learning surrogate models that can bypass numerical integration and quickly generate the velocity field of the turbulence. So this is a work led by my PhD student and our collaborators at Lawrence Berkeley National Lab. There's vast literature in turbulence modeling. So in the traditional CFD community, people usually design CFD-based methods such as Reynolds averaging to numerically solve the differential equation, which obviously takes forever. There's some recent interest in the turbulence community of physics-informed deep learning, but they're quite limited because some of them require no external force, and some of them only model the spatial dependency without considering the temporal dynamics. For physics-informed deep learning method itself, it requires explicit inputs of boundary conditions, which is not available in a situation of forecasting. So in parallel, we have fluid animation, which is the field heavily studied in computer graphics. In computer graphics, the area emphasizes more on the simulation realism, which means as long as it looks good, we're okay. But it cares less about the physical interpretation or the consistency of the predictions. There's also literature about video prediction because you can view the evolution of turbulence as a video. It's a very special type of video, which is quite different from video prediction itself that deals with noisy data and unknown physical processes. So in our work, we propose this hybrid learning framework because we know turbulence is governed by Navier-Stokes equation, which is a set of differential equations that describe the motion of viscous fluids. So we looked into the classic method in fluid simulation. And we discovered that there is this method called Reynolds averaging, which is to decompose the velocity field W over space x and time t into two components, where the first component is computed as a temporal average field of the velocity using a convolutional kernel G of S. At the same time, there's another in parallel method called large eddy simulation. It had the same idea of decomposing the velocity field W over space x time t into component, and the first component W tilde is computed as a spatial averaging using a spatial kernel G of x given C and the residual component. So this idea of decomposing a velocity field
Did we lose Rose or did I have a connection drop?
I've also lost Rose.
Likewise.
Okay. I'm sure she'll be back in just a moment.
I've seen that the GIF that Rose showed in the beginning, the one of temperature variation since whatever it is, the 70s. Every time it never fails to make me depressed about the future.
Okay, I'm back.
Hi, Rose.
I'm not sure what happened.
I'm not sure what happened either. We lost you.
We're having some turbulence.
Yes, we're having
There might be some turbulence. That's right. Okay, so we were here, right? So
yes.
We talked about, the idea of Reynolds averaging and large eddy simulation of using multi-scale decomposition of turbulence. So there is also a combined approach that combines the RANS and LES methods that leads to the RANS-LES coupling. So this decomposed the velocity field into three components using the spatial filter and the temporal filter. So that's the spatial filter G1 and the temporal filter G2. So the idea of learning trainable operator essentially is implemented as we simply replace the spatial filter and temporal filter here with trainable weights. And because it's a convolutional operator, so that naturally leads to a convolutional kernel. And this is our proposed method, which we call the turbulent flow net. Right, in this model, we take the multi-scale decomposition, where given the velocity field W, we pass the velocity field from the historical frames into a spatial filter, which is nothing but a multi-layer convolutional neural network that will give us a spatial averaged field. And we take the residual and feed that into a temporal filter, which is another convolutional neural network that give us the temporal averaged fields. And then we model the fluctuation separately. For each of the components, we use a UNet, and the UNet is a multi-layer convolutional neural network with residual connections. So we encode each of the components with separate encoders, right, to account for their multi-scale dynamics. And we use a shared decoder to model the interactions across frequencies. And this is the resulting model, which we call turbulent flow net. So we evaluate this model on a benchmark data set called Rayner-Burdett convection, and this is on 2D turbulence. The task here is to do forward prediction. So given the past 15 frames of the turbulence velocity field, we want to forecast 60 times ahead into the future. And the resolution of this turbulence is 64 by 64. So here is the forecasting results as we forecast further into the future. And this shows the forecasting RMSE, root mean square error, with respect to the forecasting steps. So we compared with a large number of baselines. So there is a turbulent net, TFNet, our model, UNet, GANs, ResNet, convolutional LSTMs. These models are data-driven deep learning models for forecasting video prediction or semantic segmentation, commonly used in computer vision community, but they don't take into any physics into account. There's also hybrid methods such as SST. So this is methods uses Green's function and approximate some part of the Green's function with deep neural network. Deep hidden physics-based model is a physics-informed neural network. As I mentioned before, this method actually needs explicit input for boundary conditions, which is not available during forecasting. And we can see that, TFNet consistently outperforms the baselines in forecasting MSE, RMSE. And most importantly, the runtime of our model, TFNet, is only half the time as the lattice Boltzmann method, which is a numerical method that was used to simulate the ground truth turbulence. So the speed up is more significant when we actually experiment with 3-dimensional turbulence. We actually saw like 1,000 to 100,000 times speed up when we work with 3D turbulence. So that shows you the promise of surrogate modeling with deep learning. But this is not the most important part, right? We show that our model can make reasonable prediction in terms of mean square error, and we can speed up numerical method. But we really care about is the physical consistency of our model's prediction. So in turbulence, we care about divergence. So we know the ground truth turbulence is divergence free. So the divergence of the predictions should be close to 0. And the target turbulence, the ground truth turbulence in the black solid line, they are close to 0. So we do want the predictions of our model to be close to the solid black line. And what we can see here is that because our method is inspired by numerical method in CFD, so it generates physically consistent predictions where the divergence is quite close to the ground truth, where all the other methods sort of fails. And then this plot is the most important plot in CFD, where we're looking at energy spectrum versus wave number. So this is also known as a Kolmogorov scale plot. And again, the black solid lines is the ground truth from the simulation. So the closer to the solid line, the better. And the two dashed lines here are theoretically calculated energy spectra. We can see that TFNet in blue and a slight variation of our method constrain TFNet with additional regularizer on the velocity divergence. They have the closest to the solid black line in terms of energy spectra. Where in contrast, the video-based methods such as the UNet and ResNet, they completely fails for small-scale dynamics. so they cannot capture the correct type of behavior when we move to high frequency eddies. Let me show you the actual prediction from our model. So the top row is the target, and then that's the ground truth. The second row is the prediction from our model, and ResNet again are the data-driven deep learning models without actually using any physics. So what you expect to see is that two circular patterns interacting with each other in a two-dimensional plane. So that's the ground truth. And if you look at the predictions of our model, it can accurately capture this rotating pattern of two type of fluids, even capturing the small scale dynamics. In contrast, ResNet only learns the smooth behavior, so it lost a lot of the small scale dynamics, even though the large scale rotating pattern is sort of correct. And GANs have similar issues. It just lost all the small scale dynamics. Again, and also because our model leverages the idea of multi-scale modeling using 3 different UNets with different encoders and shared decoder. So we also performed an ablation study by zero out all the rest of the encoders, but only let one of the encoder to make prediction. So here is the actual prediction from one of the encoders when we zero out the rest. We can see that, for example, this is the ground truth target, and TFNet is the aggregated predictions from all the 3 different components. And let's see whether the model actually learns to decompose the turbulence into different frequencies. So you can, if you look at the fluctuation, it resembles much higher frequency turbulence in the data, and temporal averaging is relatively smooth, large scale behavior, and spatial component is in the middle. So let me play the video again. The fluctuation component is much higher frequency than other components. And it shows that this model automatically learns to separate the scales in the turbulence and leads to better performance. So that's the first type of method, which we call trainable operator. And there's also other related works, such as neural Fourier operator, which is based on the same idea. The second type of approach of physics-guided AI is what I call residual learning. This is a very simple idea, which means if we still want to learn the underlying dynamics model F, right, given the input time series data, so this learning dynamics model F gives us the map from historical states, the x0, xt, into the future sequence of states, xt plus 1 to xt plus f. Because we don't know the underlying dynamics. So, but we may have some partial knowledge of this dynamics model that can be represented as differential equations. So the idea of residual learning is to decompose this function into 2 parts, where function g can be based off some physics model that are governed by differential equations, and the residual model can be learned from data. So in some sense, we're using deep learning or machine learning model to learn the correction terms of physics-based model. So, and that's when we combine together, we're learning the residual of the ground truth dynamics from the physics-based models. So that's like a really simple idea, but when we actually implement it, there's some tricky part that I want to talk about through this example of learning the turbulent effect on air robotics, on air robots, the drones. So this problem is called combating ground effect. So when we fly a drone close to the ground, because there's air turbulence that is exerted by the rotor of the drone, so this air turbulence interacts with the ground, and that will cause the drone to crash. This is the phenomenon known as a ground effect. It happens not only during landing, it can also happen during taking off. So that's a very big issue in aerodynamics control. So this work was led by my collaborators at Caltech. So again, we're taking a hybrid learning approach, right? Because when we look at the drones, we know very well how the physics works for the mechanics of the drone. Because if we look at the simplified picture, we have a body of the drone simplified as this gray rectangular box. So the drone has some body weight, and there are two rotors in green and red that generate the thrust for the drone, and together it leads to the motion. So there are some drags that constrain the motion of the drone. So in this simple model, we can record the positions of the drone P, the velocity V, and the angular velocity omega. And then we can also calculate the total thrust and the total torque of the drone, F of U and tau of U. So every variables in black are known, either known or can be calculated from first principles. But they're all known terms, such as the air disturbance force and the air disturbance torque, F of A and tau A, that are all known because we cannot accurately simulate the turbulence because it takes forever, right? And we also cannot measure them accurately with sensors. So in this case, right, we call all the measured variables P, V, omega as a state of the system. So that's a state of the system from the previous timestamp, ST-1. So in the control setting, we also have external input, and that's the control from the previous timestamp that refers to how you control, change the velocity or change the angular direction of the drone, right, through remote control. So we have a set of differential equations that governs the motion of the drone. For instance, the first order derivative of position is velocity, and all these equations can be derived from Newton's laws, and there's nothing complicated about this type of model. So again, these differential equations, everything in black are either known or can be calculated from first principles. But the part in red are unknown terms that correspond to the unknown disturbance force and the unknown disturbance torque. So based on our residual learning idea, right, because we know part of the physics from first principles, and there are some terms that we don't know, so we can probably just use a deep neural network, right, to approximate this F of A, then maybe we're done. So if we can learn this, then that can allow us to calculate the new state at the next timestamp. And then we can repeat this control loop, and we can actually fly a drone in a very stable fashion. So that was a very original idea that we tried to approximate this unknown disturbance force with a deep neural network. But we actually ended up almost crashing the drone. So the simple idea actually did not work, right? The reason for that is deep neural networks are very flexible, but sometimes for learning dynamics, they can be too flexible. So if they're too flexible, that will lead to unstable dynamics in control. So the final idea that we ended up with is something slightly different, where we need to regularize the behavior of a deep neural network with something called spectral normalization. So this is what we call learning stable dynamics. Spectral normalization is a way to constrain the behavior of a deep neural network. Specifically, we're constraining the Lipschitz constant of a deep neural network because we can simplify the deep neural network as a sequence of functional compositions. So if I have a function f of x, I can represent it as a sequence of function composition gx to gl, where each layer of g of l is a fully condensed neural network. So each function g of x can be written as a weight matrix WL multiplied by the input x applied by a nonlinearity phi. So this nonlinearity can either be a sigmoid function or a tangent function or any of your favorite nonlinear activation functions. So if we want to regularize the Lipschitz constant of this function f of x, then we need to basically regularize the Lipschitz constant of the entire sequence of function composition. It actually turned out to be a much harder problem. So it's computing the Lipschitz constant is quite difficult. It's an NP-hard problem. But luckily, we can approximate the Lipschitz constant of a function. So this picture is a visual of what Lipschitz constant means for a function. So essentially, when we look at the function here, the Lipschitz constant is the upper bound of the slope. So if we have a Lipschitz constant L, then when we look at every angle of this function, then L is always the upper bound of tangent of alpha. So we cannot calculate the Lipschitz constant of a function exactly, but we can calculate them approximately. It turns out that this Lipschitz constant of a function can be approximated as a product of the largest singular value of all the weight matrices. So we can compute the largest singular value of every layer, WL, and then multiply together that give us the rough upper bound of the Lipschitz constant for this function. So the actual implementation can be done quite simple because we can normalize the weight during training by the largest singular value. So during training, every iteration or so, every few iterations or so, we can renormalize the weights by this largest singular value. And they will constrain all the weights to have a bounded Lipschitz constant. In this way, we can regularize the behavior of this neural dynamics or the neural disturbance term. And then once we learn this disturbance term, we can plug that in with a residual model, and we can have a much better dynamics model for the drone. So let me show you the results of this method, right? So neural lander is our method, and this is the baseline called PD control, and this is a commonly used method in the control community for controlling the drone. You can see that during 1D landing or the 3D landing case, because of the unknown disturbance force, the drone cannot land on the floor accurately because it had to be very safe. So there's a gap from the target landing place and the actual landing positions. But if we look at the neural lander, because we're learning the unknown disturbance force with spectral normalized DNNs, we can see that the drone can land on the floor exactly and smoothly, no problem. So it's the same thing happens for 3D landing case as well. We can see that the drone can land diagonally from one angle to the other angle. Then we can also look at a different task, which is flying around the table, because we can actually estimate the disturbance force on the drone. So the drone is able to fly around the table much closer to the surface without crashing. But for the baseline method, because we have a lot of uncertainty of the dynamics, the drone has to be very safe and so much up to the top. So this kind of situation is very useful for disaster rescue when we want to fly a drone within a very narrow space in a tunnel or something else. We can also investigate what does spectral normalization do to the generalization ability of the deep neural network. So this plot shows the velocity in vertical distance and versus the vertical distance and vertical velocity. So z is a vertical distance and vz is a vertical velocity. So when we train our data in some training domain, right, with spectral normalization, we can see that this linear dependency actually extends into new domain, which means the model has learned to generalize to unseen scenarios. But without spectral normalization, you can see that linear dependency disappeared in the new domain, so the model failed to generalize. This phenomenon is more obvious in the flying around the table case, whereas with spectral normalization, we can see the model has learned a clear table boundary, even though we only sample a limited domain in this table, whereas without spectral normalization, then the model does not know the boundary of the table. So it actually has to be very safe. So in learning theory, we know that normalization of DNNs actually leads to stability. So generalization actually is an indicator of stability, right? So that's like the second type of method of residual learning. I guess the take-home message is that, yes, it is a very simple idea to learn the residual terms of the dynamics using deep neural network, but we also have to be careful of what kind of residual terms we're learning. So the last one, right, of how we can combine physics and machine learning is something I'm quite excited about. And this is the idea of equivariant learning. So we know that a large part of physics is built on the fundamental principles of symmetry. So the question is, how can we encode symmetry into deep neural networks so that we can preserve the physical quantities that we want? There is this beautiful theorem of Noether's theorem that connects symmetry with conservation laws, which said for every symmetry, there is a corresponding conservation law. So when we built machine learning models to make certain predictions where we actually want certain quantities to be conserved, the question is, can we build symmetries into deep neural networks to make the neural network symmetry aware? And that's the area of study of equivariant learning. So we want to learn a function that is equivariant with respect to a certain group. So by definition, that just means if we wanted to learn a function where we apply a group transformation rho of G into the input, this transformation will automatically apply to the output of this function. So in other words, f of G equals to G of X. If a function f satisfies this kind of condition, then we say this function is equivariant. So in a setting of learning dynamics, we're using the function f to approximate the underlying dynamics, and we want this function to be equivariant with respect to all kinds of transformations to the dynamics. So as an example, I can show you how we can use the idea of symmetry-aware neural network to model the complex dynamics of traffic flow, right? So as here. So you can think of traffic flow as a type of fluids, but it's just much more complicated because, it not only have the physical quantities of fluids, as we showed in the first example, there's also complex interactions of all these cars. And also there's complication resulted from human psychology because people are not always rational. They're not always making rational decisions. So this kind of fluids is much more complicated than Rayleigh-Bernard convection, where the question is, well, can we model this kind of dynamics with symmetry-aware deep neural architectures? So this is work done by my grad students and postdoc. Okay. Okay, so let's have a quick brief recap of what symmetry is. In symmetry, we have an important concept called group. A group is a set G with a composition map to itself. So identity is an element in the set, and for every element G, there is the inverse element, G inverse. A familiar type of group is a rotation group in 2 dimensions, SO2. So for every rotation, let's say if we rotate this object clockwise by 60 degrees, there is an inverse element, G inverse, which means to rotate the same object counterclockwise by 60 degrees. I already talked about the definition of equivariance and invariance, right? So if we have a function f and we have a group G, and we say that this function is invariant, when we apply the transformation G of X, it does not change the output. So f of G is equal to f of X, then this function is G invariant. And equivariance is a general definition. So when we apply a transformation G to the input, it automatically applies to the output. And if a function satisfies this kind of condition, we say that function is equivariant. It's easy to see that invariance is a special case of equivariance when the group maps it to self. As an example, let's consider the function as a scaling function of the velocity field. So we have X, which is the spatial grid. X is represented space. And this function applies scaling to the velocity. So f of X equals to X and 2V. Let's consider the group as a rotation group in 2D. So a representation of 2D rotation can be written as a 2x2 rotation matrix with cosine and sine in its elements. So when we say a function is equivariant to the rotation group, that just means, let's say we apply the transformation to the input, right? So when we rotate the velocity field by 45 degrees, we rotate the velocity field by 45 degrees, and then we apply the scaling function by scaling the velocity by 2. It is the same thing as we first scale the velocity field by 2 and then rotate 45 degrees. In other words, when we're going through this kind of transformation in the bottom left route, it's the same thing as going through the transformation in the top right route. If the set function satisfies this kind of condition, then we say the function is equivariant to this group transformation. Okay, so then the question is, well, how can we build neural networks that satisfy this kind of condition? It's actually quite simple, because we know neural networks are universal functional approximators. So if we want a neural network to be symmetry aware, to be equivariant to a particular group transformation, then we just need to ensure every layer to satisfy this kind of condition, right? So if a function is, represented as a multi-layer neural network, then we cannot change the input and output representation because that's already defined by our problem. But we can change the intermediate representations of how we can map the input to hidden representations. So in our paper, we proved that, basically if the maps between layers are equivariant, then the entire network is equivariant. Under linear actions, even adding skip connections does not change its equivariant. So this gives us a lot of flexibility of how we can design neural networks. We can even include the residual networks that are very common in deep learning. And as long as they're equivariant among layers, then the entire network is equivariant. Concretely, we can design equivariant layers through this idea of weight sharing. So this classic results, not classic, it's relatively recent, but it's a very general results of how we can construct convolutional layers to be equivariant with respect to any group G. So it means that, well, in a convolutional layer, the only thing that matters is convolutional kernel. So for a convolutional kernel, G of E, as long as satisfy this condition, which means when we apply a group transformation to the input, there's a conjugation term where we left multiply row of inverse to this kernel and right multiply by the same group transformation. If the output stays unchanged, or in mathematics, we call group invariance under conjugation, then this kernel is group equivariant. So the convolutional layers are equivariant. So because we know the group that we wanted to encode symmetries on, the only thing that's left to do is to figure out the correct representation for the group, right? The row inverse and the row in for each group. And we can design, if we can find the right representation through weight sharing, then we can construct equivariant layers. So this idea actually has been already implemented in our very familiar type of neural network, which is CNNs. Because CNNs are translation invariant, right? And that's precisely the reason CNNs are so successful in computer vision, because it captures the translation invariance in images. So in this case, we consider the symmetry group of translation, right? So we are translating, this is a bunch of pixels from one position to the other. The way CNNs implement translational symmetry is that we consider the filter in this orange block. So the weights within this orange block are freely trainable. They're free trainable weights. However, the weights across these two orange blocks, across these two filters through translation, they're entirely shared. So these orange blocks have the exact same weights as the orange block in the right corner. And the weights within the orange block are fully trainable. So by implementing this type of weight sharing scheme, we can directly satisfy this condition of group invariance under conjugation, in this case, the translation group. So we can simply just generalize this idea of weight sharing to many other groups, right, by constructing different type of representation and implementing the weight sharing scheme. And that's precisely what we did for modeling the problem of traffic flows. So our model is built on the key insights that we can resemble the traffic dynamics of many particle systems. And it has been discussed in the classic paper by Halbling in 2000. Because we can consider cars and many particles. So if we want to predict the trajectory of cars, then perhaps we can look at the internal symmetry of many particle systems. And in fact, many particle system pertains to rotation symmetry, because when we learn how to drive in the North Hemisphere, right, and when we want to turn left or turn right, and we move to a different place in this earth, right? In this world, we move to a completely different place. We still know how to turn right. So there's this kind of internal symmetry that's built in our brain. So the idea is that, well, can we build our models that can distinguish left from right turns and give consistent predictions regardless of the orientation of the intersection shown in this picture? So in the end, we ended up designing this type of special convolution called equivariant continuous convolution. So we're dealing with a continuous group of SO2, right? It's a continuous group. So we need to figure out the correct type of representation for the continuous group, row in and row out for the rotation group, governed by this parameter theta, which corresponds to the rotation angle, and R is the radius of this rotation. So to impose this kind of constraints for continuous convolution require us to develop an efficient weight sharing scheme. So in the literature of equivariant learning, there has been some work of tensor networks or equivariant CNNs for SO2 group, but they require very complex harmonic analysis and constructed, complex basis function, which is quite computationally inefficient. So in this paper, we come up with a much simpler scheme of constructing SO2 equivariant groups through weight sharing. So we use this kind of scheme called the orbit and stabilizer representation. Then in essence, we're looking at the particles in the polar coordinates, and then we focus each cars and center each cars at the center of this bullseye. And we'll look around at the particles around this car. And so we're constructing the weight sharing scheme, which means we are splitting this polar coordinate into different slices. So within the same coordinates, within the same orbit, they're all shared, but within each slices, the weights are freely trainable. So the weights are shared along the orbits, and then the weights are constrained to be a stabilizer, which is a bullseye. So this kind of resembles the weight sharing scheme in a CNN for translation group, right? Where we share the weights among the translation. Here we're sharing the weights along the rotation, along the orbits. And the weights and the rest sections are freely trainable. The only thing is a singularity in the middle, which is a red bullseye. So it has to constrain the weight matrix here, the kernel matrix, to be a circular matrix. And it turns out there's some geometric interpretation of this kernel, right? Because we're dealing with the rotation group. So this kernel, which operates on SO2, so this first element is a circle, the second element is also a circle, and circle cross circle is a torus in this picture. So this kernel, the geometric interpretation of this kernel is a torus kernel. So this kind of weights you see resulted from when we cut open this torus kernel, and we can see how this weights will change along the orbit of this, polar coordinates. So we can implement this kind of convolutional kernel into a typical forecasting framework, right? We have the positions of different cars, and then we encode them through different type of modules. So we have 3 different modules, right? And we encode the past position and velocity of all the cars. So the first module will encode the map information. The second module encode the multi-agent interactions of cars. And then the third module encode the single agent behavior. And for each of the module, we use our proposed continuous convolutional kernel to map the raw data into some hidden representation. And after that, we concatenate all the hidden vectors into a long vector, and that becomes the encoded information from the past. And then we will try to decode to make predictions. So again, we're using our proposed continuous convolutional kernel, right, to generate the map from the hidden vectors into some output. And here we're actually predicting the delta x, which is the distance displacements of the cars. And then we add the displacements to the original position that will give us the position of all the cars at the next timestamp. And we repeat this process for multiple layers to decode the future. For both the encoder and the decoder, we have our own proposed components called continuous convolution. Okay, so we can look at the performance of this model. on real-world transportation data. So Argoverse is a benchmark data set from a self-driving car company called Argoverse. So they have this benchmark data set which predict the motion of all the autonomous vehicles and the surrounding agents, including the pedestrians and other cars. And TrajectNet is another benchmark data set for trajectory prediction, which is a tracking data from videos tracking the movement of pedestrians. So here we're looking at the average distance error, which is the displacement from the ground truth, and this displacement error at 1 to 3 seconds. These are standard metrics used in the community. So we compared with some baselines, such as constant velocity, which only assumes the cars are moving at the constant velocity, and nearest neighbor, which is to predict the cars moving similarly at the neighboring particles or vehicles. And there are other methods such as LSTMs, continuous convolution. The major competitor of method is continuous convolution, which means that this is a non-equivariant baselines, where our method changes the continuous convolution to make it equivariant or to be symmetry aware. So we can see that with symmetry added to the neural network, we can predict very accurately. The error is quite low compared with all the other baselines for both data sets, right? But that's not the most important part. We also looked at the number of parameters that are needed to implement this model. So compared with the non-equivariant models, we can reduce the number of parameters in the model by 95%. This is quite important because when we want to implement this model in the embedded system, it's critical to have a very small model that is energy efficient. We also look at the sample complexity of model, which is how many data we require to train this model. So this shows the number of the distance error at 3 seconds versus the training samples. And then we can see that compared with the non-equivariant models, the symmetry aware echo model can reduce the data sample complexity by 80%. And that shows you the benefit of encoding symmetry as an inductive bias to reduce sample complexity. We also included this vector net, which is the Waymo benchmark method. So this method is not directly comparable, but we include here anyways, just for reference, because this model can only predict the motion of a single car at the same time, but where our model can predict for multiple agents simultaneously. Okay, so that's kind of the 3 paradigms that I talked about for how we can encode physical principles in deep dynamics models. And I talked about, trainable operator, which is to replace the mathematical operator with trainable weights. And I demonstrated using the turbulence flow example. Talked about the residual learning to learn the correction terms of physics-based model. And I demonstrated through the drone landing example. And the equivariant learning is to incorporate symmetries into deep neural network through weight sharing to guarantee conservation loss. And I showed the example of forecasting trajectories of autonomous vehicles. In terms of future work, and we're very excited about this direction, as you can see, we're always looking for students and postdocs and collaborators to work with us. We want to investigate stochastic dynamics and multi-agent interactions. Finally, there is a quote that I really like. It's from one of my favorite physicists. So he said, time and space are not conditions of existence. Time and space is a model of thinking. So hopefully after my talk today, I can get you to think a little bit more in the model of time and space and contribute to this exciting field of spatiotemporal modeling, right? And you can check out the code and data on my website or follow me on Twitter. I want to thank all the agencies for providing the general support for this research.
All right. Thanks a lot, Rose. Are you still there?
Thank you.
Yes.
Yes.
I was worried for a second that we lost you again. Thank you for the wonderful colloquium. It was good to hear about your work and cool to see so many different aspects of it in one talk. I'm sure that was useful. So now is a time where we're going to take questions from the audience, and there's one from YouTube that I will synthesize in a second and read to you. But if there's any questions from the audience, please raise your hand and Marisa will call on you. I see Jesse with his hand up.
Great. First, thanks, Rose. That was a great talk. So you mentioned about having the difference between getting the physics right and whether something looks right. And I'm curious, to what extent does that depend not just on the neural network architecture, which is what you focused on, but also on the choice of loss function. Do you have to do anything in terms of the loss that you use to make sure, for example, in your turbulence example, that you got the right scaling behavior? Is there something about the loss that also matters in this?
Yeah, that's a fantastic question. So the very first idea we thought about, enforcing the divergence-free constraints is through loss constraints, right? Because we can literally just add a regularizer to constrain the predicted velocity to be close to 0. But there is actually a counter effect, because when we actually enforce this kind of loss constraint, the predicted velocity becomes very smooth. You just it's averaged out the prediction of the velocity field. So that just shows you well, so obviously you can add constraints to change the loss function to enforce some type of physical consistency that you want. But because, there are different objectives that we're trying to optimize, sometimes there are counter effects that we might not desire.
Great, thanks.
Mm-hmm.
Max has a question.
Yeah, great talk again. In the example that you had with the landing drone, what kind of sensor data did you have? Did you have just accelerometers, or were you also measuring positions?
Yeah, so we have basically kind of the sensors and touch this distance room, right? So we can track 3D positions of the drone, and we also have accelerometer, different kind of IMUs and all these sensors that can measure the kinematics of the drone.
Okay.
I'll read one of the questions from YouTube, which sounds like a question about data augmentation versus architecture design. How is taking this rotational symmetry in the EchoNet different from giving the inputs some rotational symmetry transformations before network training? And this is from Aman, who's a physics major undergrad.
That's a great question. So actually, if you go to our paper, we have additional table that shows adding data actually is not better than using, symmetry aware architecture. So we actually compared with data augmentation, right? But in general, yes, that's true that you can augment the data. And one is that it's simple to do, right? Two, that's what people do in practice, because, constructing the correct equivariant net is not trivial. So, but I would say well, one is that if you have more data, it takes longer to train. And two is not clear what's the best way to add data for a continuous group, right? Because there's almost infinite possibilities. So you can rotate the data and add it to it. And especially for cars, there's no canonical reference frame. So it's difficult to figure out what's the right way to augment the data.
Very good. That was a very clear answer. Thank you, Rose. Mm-hmm. Other questions out there amongst the participants? I had a question, which was sort of earlier in your talk when you were talking about TFNet versus ResNet, and you showed that your architecture captured the small scale dynamics in a way that the other architectures just did not, and it really matched ground truth in that regard. Could you, I think you said it, but could you review again, what was it about this architecture that helped it capture the small scale dynamics so well?
Yeah, so that's a very good observation. So basically the key idea is multi-scale spectral decomposition, right? We took this idea of TFD method, which is Rens-LS coupling. And that idea is based on multi-scale spectral decomposition, because the turbulence have, multi-scale dynamics. So if we can model each scale separately, right, and also model the shared interactions across scale using our shared decoder, it's much more efficient than just use a huge neural network like ResNet or convolutional LSTM to directly model the velocity field.
So you're getting more direct control over the multi-scale dynamics.
That's right.
By architecture design. I see.
That's right.
Great. Aman chipped in from YouTube and said that was a great answer. Thanks for being so clear responding to this question.
No problem. Thanks for the great question.
I saw another hand up. Peter.
Hi, yeah, thanks for the great talk. I think, so I guess I had kind of two questions on, well, one on one of your different areas that you're presenting, but the first one was just maybe, why does it make sense to separate in the turbulence example the temporal filter from the spatial filter? Why not just do them together?
Oh, I guess you can, right? Because if you just use, the same architecture, then it just corresponds to different frequencies. I guess the LAS coupling, Rand's LAS coupling is some method that people commonly use in CFD.
Okay, thanks. And I guess the other one was just about this equivariant networks. I know there's been a lot of work in this area, like for like quantum chemistry, for example. Can you compare maybe the method that you described with some of these other approaches that I think are also similar, like they use these convolutional, they have like an architecture that's based on convolutions over arbitrary groups, like rotation groups. Is it the same kind of method, or is there some distinction between this and the methods, for example, that they use in these like quantum chemistry kind of tasks?
They're very related. Like as I mentioned, right? So SO2 equivariant network was probably already published in 2019 and even maybe 2018. So they were using very complex harmonic analysis to like compute the Clebsch-Gorban decomposition. It's very computationally expensive. And then actually after we published our paper using like orbit stabilizer representation, Max Wellin's group and some others published a new paper this year at ICML, which they discovered this much simpler way of computing the convolution in a continuous space, and the actual formulation is exactly the same.
Great, thanks.
Mm-hmm.
Peter, is your hand still up, or is that a new hand?
Oh, sorry. Let me, yeah.
Right. I'll ask another one from someone else on YouTube. Can we apply a harmonic transformation, a Fourier transformation in polar coordinates before we apply the CNN for a rotation symmetry?
How do you actually apply harmonic analysis to each particles? I'm not, I on top of my head, I cannot think of how to do that. But if you have more insights, maybe you can email me afterwards.
And there's a 20-second delay on YouTube, so there's no way in real time to to go back and forth, unfortunately. But I'm sure they'll email you if they have more questions about it. Any other questions out there?
There's one in the chat.
Oh, thank you. Yes, Jose, would you like to unmute yourself and ask?
Hello, everybody. Yeah, I wanted to ask, like, so these seem very specific for physics. Are these possible to apply in other contexts? These ideas?
Oh, yeah, we have applied these type of ideas to a range of different applications, like due to time constraint that I didn't get to talk about them. We have seen success of, using this type of hybrid methods to model COVID-19, right, to forecasting ocean currents, to even model the behavior of robots. And yeah, so, and as somebody else mentioned, this idea of equivariant learning has been applied a lot in quantum chemistry for predicting molecular dynamics. Yeah, so I don't think the examples here that were listed are the only examples you can apply this method for.
Okay, thank you so much. And it was really nice, the presentation.
Thanks.
I liked it.
Presumably, as organizer of this colloquium series, that's where I should jump in and say, yeah, it's exactly that sort of idea that you're getting at, Rose, that these ideas that are natural in physics that you're bringing back into physics with machine learning also are just sort of general machine learning techniques that you can apply to all different sorts of data, right? It's really, your physics-inspired AI is absolutely applicable in all these other regimes. That's very much in the spirit of what the entire institute is about and what we're about here. So, excellent. Any other questions out there? There was one more practical one from YouTube that, since we have a minute, maybe I'll ask, and then all the YouTube questions will have been covered. I think that's a first. So Aman, this person who asked a question about symmetries, asked about residual learning and whether it also gives, in addition to an accuracy improvement, a speed improvement relative to the trainable operator approach, as physics modeling is still a part of that structure. Does it give a speed up?
Could you repeat the question again?
Yeah, so
the last part.
I'll try to read it rather than paraphrase. So his question is, does the residual learning approach also give a speed improvement like the trainable operator approach, as the physics model is still a part of it?
Oh, I see. That's an interesting question. I think it just depends, because a trainable operator, it does not require physical model, right? Because it's directly replace the mathematical operation with some trainable weights, and during inference it's very fast. With residual learning, because we actually rely on simulations of physics-based models, so it can be, it sometimes can be time consuming. And that's what we observe in COVID-19 modeling, because we're just dependent on the actual physics-based models.
Excellent. Wonderful. I'll give it one more second in case other people would like to ask a question. Any last questions out there for Rose? All right, well, in that case, let's thank Rose one more time for the wonderful colloquium. It was great to see you again, and hopefully we'll be able to see you in person before too long if numbers get better here.
Absolutely. Absolutely. Thank you, guys. You guys are a great audience.
Really wonderful, and we will post your slides and your talk online, and I'm sure that other people will email with questions. So thank you very much.